This week's lab covers thermotropic liquid crystals, and of course this is a nanoscience lab. So first of all, let's talk about self-assembly. Self-assembly is the process in which a disordered system of pre-existing components forms an organized structure or pattern as a consequence of specific local interactions among the components themselves without external direction. When the constitutive components are molecules, the process is termed molecular self-assembly. And another way to put it is the nanostructure builds itself. So in today's lab, you're going to be using these self-assembled liquid crystals. So what is a liquid crystal? Liquid crystals are examples of self-assembled molecules. We call them the fourth state of matter or another state of matter. I kind of think of them as an intermediate state of matter. Liquid crystals flow like a liquid under certain circumstances, but they have long-range order like a solid, so it's kind of considered soft matter. So if you look at this little diagram over here, liquid crystals will first come in the solid phase, and then as they are heated, they will transition into this liquid crystal phase. In the liquid crystal phase, they can flow, but because of their structure and the electrical interactions in between neighboring molecules, what will happen is that they'll have a fixed orientation with respect to one another, but their positions will be able to slip and move past each other randomly like a liquid. And then, of course, if they get heated up even more, then you have basically a true liquid phase with random orientation. So a liquid crystal phase of matter has got to be at an intermediate temperature. If it's too cold, it acts like a solid. If it's too hot, it acts like a pure liquid. So at these intermediate temperatures, you kind of get the best of both worlds. So what happens is these liquid crystals are made of these molecules, like you can see here in the picture. And the molecules can either have kind of a cylindrical structure to them, like the one on the left, or more of a plate-like structure, like you see here on the right. Okay, and then what happens is, because of the way that they interact with one another, the molecules in the liquid crystal can align. So if they're in a solid, then they're frozen or fixed in position. But as they heat up, they kind of order and stack in a specific direction. And yet within that direction, they're not locked into their particular position. They can still flow and move around one another in response to a disturbance, for example. Okay? Now these liquid crystals are abundant in living systems, in cells. They form cell walls, lipids, and things like that. But today, we're going to deal with some that get used in liquid crystal displays. Now the thing is, if it's in that intermediate liquid crystalline state, then a small perturbation or a small change can modify how the molecules are self-assembled. Okay, so they can change their molecular and their supramolecular organization drastically as an effect of a very small external perturbation. In today's experiment, we'll show how a relatively small change in temperature can change the structure dramatically enough to change the color of the liquid crystal. So this external perturbation will cause that liquid crystal to change phase, and these different phases in today's experiments can be distinguished by their different optical properties. Like I said, they're going to change color. Now, speaking in a large sense, there's three different groups of liquid crystals: lyotropic, metallotropic, and thermotropic. In today's experiment, we're going to look at thermotropic liquid crystals, where the structure changes with temperature. But to define the other types, we talked about thermotropic. Lyotropic liquid crystals are going to be able to change phase with temperature or concentration of the liquid crystal in some kind of solvent. And then metallotropic are going to be molecules that can change their phase with varying temperature, concentration, and then ratio of organic to inorganic compounds in the liquid crystal. So as you can see, most of the liquid crystals, the thermotropic and the lyotropic, are organic molecules. Of course, that means that they're composed of carbon. But the metallotropic, you can have organic and inorganic molecules. And then the organic-inorganic ratio can also change the structure and cause phase changes. Okay, So let's focus in on today's experiment, which is with thermotropic liquid crystals, and they exhibit a variety of phases as the temperature change. As I said earlier, if the temperature gets too high, way too high, then any long-range or short-range order is lost and it acts just like a real liquid. And then, of course, on the other end, if it's really cold, very low temperatures give a crystalline structure, and so it behaves purely like a solid. But it's at those intermediate temperatures where you get the liquid crystalline behavior, okay? So you'll have some order, but that order gets progressively lost as the temperature is increased. And what I mean by that is kind of shown here on this diagram. You can see that there's a transition in the picture from cold temperatures where it's crystalline to what's called a smectic phase, then a nematic phase, and then finally the liquid phase. So what are these intermediate phases? Well, in a smectic phase, the molecules are going to form layers, as you can see in the picture. And in this picture, you can see that they form the layers, and the long axis of the molecule, all of those long axes of those molecules are parallel to one another, but then they're turned and inclined slightly with respect to the next layer, as you can see. Okay, so that's a smectic phase. The nematic phase is shown here at the picture on the right, and that's when it's slightly warmer. In the nematic phase, the molecular axes are all parallel to one another, but you can see that it's no longer forming these nice ordered layers. So it's a little more disordered than the smectic phase, but it's not quite the same as a liquid phase, where all of these axes could be rotated with respect to one another. Okay? Okay, so to sum up, the smectic phases, molecules positionally ordered along one direction, and in the nematic phase, those molecules no longer have positional order, but they have long-range orientational order, which means that the molecules themselves move randomly, not staying in layers, but they all point in the same direction within the domain. Okay, so that's what you can see. Now, in today's experiment, we're going to deal with a particular type of liquid crystal, and that's one that forms a chiral nematic phase. Okay, so the chiral nematic phase exhibits chirality, and of course, chirality means handedness. So if you think about how screws are oriented, like regular, screwdrivers and screws, then they have a certain chirality to them, where we develop screws to be right-handed. Okay, so that when you twist them to clockwise, then the screw screws in, and if you counterclockwise, then it comes out, righty-tighty, lefty-loosey, right? That's a handedness to it, okay? Now, sometimes this phase is called the cholesteric phase because it was first observed for the cholesterol derivatives, like you're going to deal with today. You're going to be dealing with 3 different cholesterol compounds. So what happens in this phase is that they stack in these rotating layers, as is shown here in the picture, kind of like a spiral staircase. And then in each step of the staircase, the molecules are arranged in a specific order, but then there's an angle in between each step, as you can see. So here's the dark blue, and then the purple on the next layer is slightly oriented, turned with respect to the dark blue, and so on and so forth as you go up to the red. Okay, that's also shown here with the vector n hat, which is pointing along the long axis of the molecule, and it rotates as it goes up. Now what this does is it creates a screw, and just like in a screw, you've got a pitch. Remember that the definition of a pitch is the distance in between neighboring stair steps, I guess, as you move up vertically. So the chiral pitch refers to the distance over which the liquid crystal molecules undergo one full 360-degree twist. Okay? So, to continue, when light strikes the liquid crystal, some of that light gets reflected back, and what you see is the reflected light. So the color of the reflected light depends on how tightly twisted that helix is. It depends on the pitch of that helix. If the pitch in the liquid crystal is on the same order of the wavelength of visible light, which is of course between 400 for the blue light and 700 to the red light, then interesting effects are seen. When the helix is tightly twisted, its pitch is smaller, and so it reflects smaller wavelengths towards the blue end of the spectrum. And when the liquid crystal is less twisted, it has a larger pitch, and so it reflects those larger wavelengths towards the red end of the spectrum. Now, if you increase the temperature of your liquid crystalline material, it leads to a decrease of the pitch, and that increases the temperature, by increasing the temperature of the liquid crystal, you see the color change, okay? And it goes from the red to the blue. So, red to orange, yellow, green, blue, and violet as the temperature increases, okay? And so this gets used sometimes in thermometers and liquid crystal displays in applications. So these liquid crystals are examples of self-assembled molecules which change their spatial organization independent of external factors like temperature. And self-assembly is a core fundamental concept in nanoscience. So this lab is showing you that the property of materials at the macro scale, the color, for example, are affected by the structure of the material at the nanoscale. Okay? And this is what nanotechnology is all about. Changing the material's molecular structures. They're too small to see, but that causes changes in the material properties, and an example of that are these thermotropic liquid crystals. So the goal of nanotechnology is to take advantage of peculiar properties of material at the nanoscale to engineer new materials with tailored properties. So let's meet today's cholesterol derivatives. Here's the three that you're going to be working with today. Cholesterol benzoate, cholesterol allyl carbonate, and cholesterol pelargonate. Okay? So you can see here why they might do this long tubular ordering that you can see here. You can see that there are all these long chain molecules. Okay? Now all of these chemicals are used in hair color and cosmetics, and they can also be found in liquid crystal and displays. The oldest one, the oldest discovered one, is cholesterol benzoate, and it was found in the 1880s. And in 1888, Otto Lehmann actually coined the term liquid crystal, in part because of work that was done with cholesterol benzoate. So what you're going to do in today's lab is you're going to take these three compounds and make different types of liquid crystals. And by type, what I mean is that it will respond to color. It'll turn to distinct color in these temperature ranges here. And you can see that all of them are right around room temperature to a nice hot day here, from 17 to 40 degrees Celsius. Okay, so each one of these different liquid crystals will respond by changing color to a signature color at each one of these temperatures. And you can see that what you're varying is the ratio of each one of these cholesterols with respect to one another. What you see in the column is the ratio, but what I want you to do is to mass out this amount of each compound in grams. So this is 0.65 grams, this is 0.25 grams, and this is 0.1 grams. And that'll be one sample that you create of the type 1 liquid crystal. And then so on and so forth for the type 2, 3, and 4. All right? So you'll mass those out, and then what you'll do is you'll take, these will be solid when you get them because they're, quote unquote cold, right? These are all going to be solids. And then you will mass them out and put them together into a little container here, a little glass container, and you'll mix them up, okay? And then you'll melt them, okay? So you'll put them on a hot plate or use a heat gun and melt them together. And you can see that when they melt, they form this kind of clear looking liquid that you see here. Now, when you have the clear looking liquid, you can experiment with it and look at the color change while it's in your container, and I want you all to do that. And then heat it up again if you've cooled it down to look at the temperature change and it solidifies. Just heat it up again, and then spread it on some contact paper, and then mush another piece of contact paper down on top of it, and then label it with which type it is, 1, 2, 3, or 4. All right. Now what you've created is a thin film of your cholesterol, right? And then you can submerge that thin film in a water bath, or even just get it to change temperature by pushing on it with your fingers. Okay, and you can see temperature changes sometimes with that on the low end for the type 1 and the type 2s. Okay, so that's the experiment that we're going to do today. So let's talk safety. You're going to work in groups of 3. We're going to have 4 groups total. Each group is going to make and test one of the types, and then all of the groups are going to hopefully test each type so that everybody gets experience with all the different ones, okay? And all groups are going to share data. And so your lab report, I want all the data from all the groups in the lab report. And of course, if time allows, you can test each one. Now, these are pretty safe compounds. As you saw, they're present in, makeups and things like that. So they're pretty safe. But of course, when they're in the makeup, they're not, concentrated. So the cholesterol benzoate is very safe. It's not classified as a hazardous material at all. The other two on the MSDS are listed as possibly causing skin irritation and respiratory and gastrointestinal tract irritation. So, of course, don't eat it, but also don't inhale the compounds. So when they melt and things like that, don't stick it up to your nose and give a big sniff. Don't sniff the compounds, because it can cause some irritation if you do that. But other than that, it should be a very safe experiment. Just to be safe, though, I am going to want you to wear gloves and eye protection during the experiment, and long pants and closed-toed shoes are the norm for chemistry labs. And if you have long hair, please tie it back. So that's going to be the safety that we do. If we end up having time, we might even be able to do this little activity here at the end, which is kind of fun. So you can make a room thermometer out of it. What you can do is cut different letters, nano, out of the types 1, 2, 3, and 4, and then kind of mount that in between some layers here of poster board, and then mount it up, and then you can take it kind of safely around and lay it on different things and watch it change colors. If you're familiar with the thermometers that they sometimes use for kids, where they put a sticky thing on your forehead, or if you have a sticker and you stick it on the side of your fish tank and it's a color changing thermometer that way, then that's what these are. These are thermometers that change color with temperature. So if we have time, we'll do that because it's fun. And it'll last about 3 to 6 months with it being in the contact paper like we're going to use. Okay? So be sure to read through the full lab posted, and this is your pre-lab, so make sure to read through all that and take the lab quiz, and I'll see you in lab.